Hello, everybody. First of all, I would like to say that not only Philippe will be retired, but I will also be retired when Athena launches at the pace we go, talking about launch in 2034, which is 1 year after my official retirement date. I hope I will be still able to participate to this endeavor, which started a while back for me. But today I'm going to give you a brief overview of Athena, where do we stand, and hopefully we will get out of this day with new ideas for the science to be done with Athena. That's a talk that I'm giving on behalf of many people, the Athena Science Study Team, the Athena community, certainly the XIFU Consortium, and I would like to take again the opportunity to thank NES, which has taken the responsibility of XIFU overall on behalf of the XIFU Consortium. So I would like to start with my conclusion in case you need to go out to get the coffee. You can after this. So Athena is indeed your next big X-ray observatory. This is a flagship mission of ESA, which will come with contribution from NASA and JAXA. It is designed to follow the two great observatories that we have today, XMM Newton and Chandra, and it will also fly after the CRISM mission, which is a small Japanese and US mission, which will bring high-resolution spectroscopy in space for the first time, the second time, but for the first time, hopefully, during the nominal mission lifetime for the mission. I think Athena has indeed revolutionary capabilities. It will perform especially result high-resolution X-ray spectroscopy with the XIFU. It will perform wide-field imaging with WFI. It will carry the capability to observe bright sources, very bright of the brightest sources in the sky with excellent spectral resolution, 10 eV with the XIFU and CCD-like resolution for WFI. It will also enable the transient sky to be observed. We will have a short response time, a few hours response time to trigger on TOOs. Athena will fly at the same time when large ground-based and space-based facilities will be operated, CTA, ESO telescopes like the one at the focus of the ELT, neutrinos, gravitational waves from ground and space, and radio and optical and so on observatories. There are synergies that we are working on with these facilities, and those synergies will likely lead to key programs that will have to be executed by the observatory when we fly. Athena is now moving to a critical milestone, which is what we call mission adoption. That's when ESA is authorized to launch the big industrial contracts with industry to build the science module and the spacecraft. And that's also the time when we will freeze the mission performance parameters. And those will lead to the writing of the so-called Red Book, which is needed for mission adoption and which we hope to deliver to ESA by the end of next year. I would like to thank PCMI today for organizing this workshop. And I think we need to prepare the scientific exploitation of Athena along the interest of the Programme National. I mean, there are a lot of science that we can do, which are probably of interest to PCMI. And I would like to say that we are preparing a school, a thematic school on Athena. It's being now in the last stage of selection, I would say, and obviously our goal is to involve all the national programs to set up the program of the school and also define the goals of the school. So what is Athena? So first of all, it means Advanced Telescope for High Energy Astrophysics. It's flying after XMM and Chandra indeed. It's the second large mission of the ESA Cosmic Vision Science Program. It will fly after the JUICE mission and before the LISA Gravitational Wave mission, for which we hope that we can operate simultaneously. It is an international mission with contribution from NASA and JAXA on both the mission and the payload, and it's dedicated to what we have called the hot and energetic universe, but to enable these science themes to be addressed, we have a very powerful payload which will be of interest in many fields of astrophysics, from stars, galaxies, planets, and all this is packed in what we call the observatory science of Athena. So Athena is, first of all, a large X-ray telescope, as large as the fairing of the launcher can allow. It will have two focal plane instruments, a wide field imager, which is led by Paul Landroy from Max Planck in Munich, in Garching, and the X-ray which I am leading. The focal plane instruments are fixed on the science instrument module, and it's the telescope which tilts and which moves from to direct the focal beam into one of the two instruments, and this telescope has also the capability to change its focal length during operation. So, as I said, it's going to be a very powerful observatory for a worldwide community, which will access the observing time through a GEO program with the selection of the proposal by a time allocation committee. So if we were to summarize what Athena is, it's big, large images with hundreds of sources, as shown on the left-hand side. This is a simulated image with the wide field imager, where you have point sources, which are AGN, accreting AGN, and you have diffuse sources, which are clusters, hot gas of clusters of galaxies. So this is this 40 by 40 arc-minute images in which we will hopefully find the first low mass supermassive black holes in the very distant universe. And the counterpart of the Earth image is an X-ray spectrum, as shown on the right-hand side. This is an X-ray view spectrum of 1 pixel of the image of the Perseus cluster, in which you have a broad Bremsstrahlung continuum, and on top of which you have hundreds of lines associated to metals. And from the line properties, we can measure a lot of the physical parameters of the plasma, including the abundance in metals, as I will show a little bit later. So hundreds of sources in images, hundreds of lines in spectra is what summarizes the best Athena, I would say. So, as I said, Athena is dedicated to the hot and energetic universe science theme. For the hot universe, we want to understand how the universe has evolved from the dark ages to today. And for this, we want to track the formation, the dynamical and chemical evolution of large-scale structures from the first galaxy groups formed at redshift of about 2 to the massive clusters that we have in the local universe. And for this, the X-ray probe, the unique probe that X-rays offer is this hot gas, which is falling in dark matter potential wells. And with XIFU, but also WFI in particular, we can access all these key physical parameters of this gas, like its density, temperature, velocity, motions, bulk motions, abundances in metals, but also surface brightness. So here you have on the left-hand side simulation, cosmological simulation, which shows that the distribution of dark matter in blue and the distribution of gas in orange, and at the node of this cosmic web, that's where we have this hot gas in which galaxies are diving. And on the right-hand side, you have simulation, WFI simulation, XIFU simulation of 9 pointings of this hot gas, where we measure the bulk motion speed of this hot gas. And as you can see, with XIFU, we will be sensitive to very small speeds of the order of few tens of kilometers per second. And as you can see in this image, we will see this non-homogeneity in the bulk motion of this hot gas in clusters. The white dots are those AGNs, background and foreground objects, which are removed from the images. It's not dead pixels of the instrument, of course. The second topic, which is relevant to this audience, I hope, is the chemical evolution of the universe. Here we want to understand by which mechanisms the metals were formed in the universe. And here we want to use these emission lines from this hot cluster gas. And we want to take advantage of the fact that this hot gas is really gravitationally bounded in the cluster. And here you have on the left-hand side at the bottom, you have an iron abundance map of this of a cluster, again in 9 pointings, where you can see also different abundance patterns in the gas. And what you want to do from these abundance ratios of different metals, you want to understand or to constrain the different channels for producing these metals. I don't want to go too deep, but there are different channels which are very efficient in producing those metals, either IGB stars, core collapse supernovae, supernovae type 1a, and of course their contribution can be, their relative contribution to a given metal or element can be constrained from the abundance maps that we will measure with XIFU. Now the hot universe is the physics of this hot gas, and the energetic universe, on the other hand, is more or less focused onto black holes, understanding how black holes work, how the central engine works, and also how those black holes shape the universe at galaxy scale, cluster scale, and so on and so forth. So we want to probe here the accretion and ejection mechanism around black holes, and we also want to check to constrain the physical process in which those ejection and accretion and luminosity produced by the black hole interact with the surroundings. So what we want here to use, again, the unique probe is the hot gas in cluster, which is shaped by the black hole activity, either, I mean, also in the cluster, of course, but also at galaxy scale to explain, for instance, the M sigma relation. And the other probe that we want to use is this accretion-powered X-rays, which are generated very close to the central black hole. And we want to do that at all redshift across the mass and luminosity scale. So here you have a black hole accretion disk on the left-hand side, at the bottom left, where you have an accretion disk and the torus, and here you have an X-ray spectrum of one of these accreting black hole, which has many interesting features. There is a relativistically broadened iron line due to the reflection of hard X-ray source on the accretion disk close to the black hole. And this line is shaped by relativistic effects, and from the properties of the line, we can constrain the spin of the black hole, for instance. And you have also absorption features in the spectrum, which are either located, I mean, absorption in material along the line of sight, and with XIFU, we will be able to determine very precisely how many of those absorbers are located, but what's their ionization, column density, and so on and so forth. This will really give us some deep insight on how black holes work, how they are powered, and how they are interacting with their surrounding. As I said, there will be additional science coming for free. XIFU and WFI will be used to study solar system planets, stars, supernovae, binaries, and hopefully new physics. And we will, for instance, be able to look at the interaction of the solar wind with planets to search for auroral and disk emission, for instance. But we will also look at ultra-fast outflows from the brightest sources of the sky. And in this case, you have a nice simulation of the spectrum of an ultraluminous X-ray source, where you have all the information contained in both emission and absorption lines. And from this, the properties of the line, you can really constrain the outflow, the properties of this outflowing gas, which can reach a significant fraction of the speed of light. So this is just to give you a glimpse of what Athena will do in short. So the payload, as I said, is split between big mirror. The mirror is under the responsibility of ESA. It's based on silicon pore optics with key requirements, 1 keV effective area, as large as it can be, 1.4 square meter. But one of the key requirements is the angular resolution of 5 arc seconds, which we estimate being the half energy width. As I said, the mirror can tilt and change its focal length, and it's going to be an assembly of 600 mirror modules in petals. So the idea is in the collecting power of emission is what, of course, gives the scientific performance of the instrument at the focus of the mirror. And the goal of Athena is indeed to provide 10 times more effective area collecting power of photons at 1 keV compared to XMM Newton epic PN. It's much more compared to Chandra ISIS. And this is nice picture of the mirror assembly. As I said, there will be 600 mirror modules, and this high technology silicon pore optics will be assembled in mirror modules like this, and you have many millions of pores which will direct the focal beam to the two instruments. The wide field imager is based on it's based on depth-fed technology. It's what we call active pixel detector. The field of view is really huge. I will show you what it means later. It has a small pixel size to oversample the point spread function of the optics. We'll have a spectral resolution better than what we have today on XMM Newton. It will also have a small detector to observe the very brightest sources of the sky. And this is a consortium, European consortium led by MP with many European partners. So this is an image of the wide field imager. We'll have 4 chips to provide the field of view, and this small detector, and this is the mechanical layout of the wide field imager at the moment. XIFU is based on microcalorimeters, transition edge sensors, which will offer this amazing spectral resolution of 2.5 electron volt up to 7 keV. It will have a modest field of view compared to WFI, but incredibly large for such an instrument. 5 arc minute equivalent diameter with pixels of the order of 5 arc seconds each. It's complicated by the fact that we will look at fan diffuse extended sources, which have low surface brightness, and therefore we need to actively shield the prime detector with a second cryogenic detector below this to screen out the background. We will have the capability to observe bright sources thanks to the defocusing of the optics, which will spread the PSF over a large number of pixels. It's a cryogenic instrument, which we have to cool down the detectors to 50 milli-K by a multi-stage cryogenic chain, long lifetime, no helium and so on. So it's mechanical coolers, and the consortium is led by France with strong leadership from CNES to lead this development. And this is a view of the XIFU cryostat, and at the center of the cryostat you have the focal plane instrument, the focal plane assembly. And just to give you an idea, we have about 3,000 pixels at the moment for the 5 arc minute field of view. And the size of the chip with this 300 pixel is about 1.5 centimeters square. And to cool this down and read out those pixels, we need to have around this very small chip. We need to have about 1 ton of cryogenic chain readout electronics. So it's a big challenge, and I'm thankful to CNES to take the challenge on board. It's a large satellite, big one, 7.2 tons at least. XIFU is 1 ton, as I said. Focal length going to be 12 meters. The total height of the satellite is 15 meters. It will be still an agile satellite. It can respond to TO within a few hours to look for instance at distant GRBs and do multi-messenger alerts too. The mission lifetime is 4 years, but the satellite should enable to live, and the instrument should enable to live for 10 years, and it's going to launch in 2034 by Ariane 6 to L1 orbit, payload orbit, first Lagrangian point for a stable and known radiation and background environment. So this is a view of the satellite. and it's as big as Ariane 6 can accommodate, really. The key performance are twofold, I would say. We want to take advantage of the combination of a large mirror and the wide field and the large wide field imager, large field of view of the wide field imager. And this is what we consider for the wide field imager, a good way of representing what WFI means. This is the survey speed, which is given as the number of sources in the images for different exposure time, and the leap in sensitivity of our current or planned facilities is that we will detect 8 times more sources in 7 times shorter exposures with WFI compared to Chandra. And of course, we will go as deep as we will be limited by the confusion limit, which depends on the angular resolution, of course, but at the moment, the ultimate confusion limit is of the order a few times 10 to the minus 17 Hz per second. And for XIFU, the key performance parameter is what we call the weak line sensitivity, which is a convolution of the effective area of the instrument and the spectral resolution. And here what we want to do is to achieve a 10 times better weak line sensitivity compared to the CRISM high resolution spectrometer. That's one way of quantifying what Athena means compared to existing facilities. And of course, compared to CRISM result, we will have also the capability to look at very wide sources. So I was digging in the science requirements of the mission, and I think of interest to PCMI. There are already identified scientific objectives that may be of interest to the program. We will, it's not an exhaustive list, but I would say maybe you could be interested by IZGRBs, which we will use as light to determine the abundances of the medium in which those very massive stars explode. We will also look at novae and planetary nebulae to determine the composition of the ejecta. We will do also the chemistry of the cold ISM. We will probe dust scattering halos. We will be able to do the physics of the warm and hot ISM, and of course, with XIFU, we will also map with unprecedented details supernovae remnants to constrain, of course, the explosion models, but also determine precisely the abundances of in young galactic supernovae remnants. I know that there is one talk where this is going to be discussed, and I invite you to listen carefully to what Elisa Costantini has to say, because it's really breakthrough science. But maybe there are some other scientific objectives that are not listed in the Athena science case, and it's not too late to inject those, and including for the Red Book preparation and for the special issue papers published by ANA, which will come in support of the mission adoption after mission adoption. So please, new ideas are always welcome. So what is the current status today of the mission?
So you have a couple minutes now?
Yes, that's done. Yeah, I'm done. That's my last slide. I would say both WFI and XIFU are designed against their original performance requirements. So no, we have not been yet subject to descopes on the instrument side. On the other hand, for the hello? Someone said something? No? Should go. On the other hand, for the optics, we have a bit of an issue. It turns out that 5 arc second is very challenging for this technology, and at the moment we seem to be converging with a sailing of the order of 10 arc seconds. This is twice the 5 arc second angular resolution requirement. There are a few cards to play now before mission adoption, and hopefully some miracles will happen. But at the moment, we seem to get stuck to around 10 arc second. Even ESA communicated to the SPC that they believed at some point that 8 arc seconds may be feasible, but this is maybe not the case anymore. So let's hope for the few iterations needed before adoption, planned before adoption, to see where we stand. At the moment, we have performed a sensitivity analysis of the survey objectives, wide field imager survey objectives against the degradation of the angular resolution. And it's very likely that the first scientific objective which will be hit by this is the IZ low luminosity AGN, which we wanted to detect and characterize as the seed for the supermassive black holes that we have identified in the not so distant universe. For XIFU, the damage is not as bad. We are more or less insensitive to the angular resolution for our scientific objectives up to 8 arc second at least. But on the other hand, we are more affected by the shortfall of effective area of these optics because there's also an issue of effective area, which is this collecting power that I was referring to. ESA is having difficulties in coping with the requirement, in particular at 7 TeV. But I should say that there are technology activities going on to recover the shortfall, and I am hopeful that we may have a reasonable shortfall for mission adoption. For the two instruments, I think the key technologies are in the past to being demonstrated for mission adoption. I think the spectral resolution of XIFU, for instance, has been demonstrated with the lab electronics and with some already identified margins. So this is a very positive development. And as I said, 2022 is going to be the time when we prepare the Red Book for mission adoption. And I think you should be also engaging if you want, if you can, for the community papers, which will be a special issue of astronomy and astrophysics, which will come after mission adoption, which is now scheduled for February 2023, pending SPC formal communication. So I think I don't have, because I started with my conclusion, I can go quickly to the end of my talk. Thank you.
Thank you, Didier. So I have a couple questions. So one question from Hélène Sol. What is the timeline for defining Athena key projects? And do you anticipate that some key programs will include a multi-wavelength or multi-messenger coordinated observations?
That's a good question. I should say that the key programs will be related to the core scientific objectives of Athena or of Athena as they were defined in the Hot and Energetic Universe science team that was selected in November 2013. But those key programs will be defined, I would say, by an ad hoc committee appointed by ESA a few years before launch, maybe 3-4 years before launch, to accommodate any changes in the astronomical landscape since 2013. So at this stage, there will be probably room for key programs coming out of some recent and exciting developments. And on the top of my head, I don't want to bet anything, but certainly multi-messenger astronomy would be a serious contender for a key program. We cannot say much. All this will be defined a few years before launch, but certainly multi-messenger will be a serious contender.
Thank you. So I have another question from Jérôme Petit. How will the time be distributed between key large programs and standard programs?
The observatory will have 4 different observing times. I should say that there will be guaranteed time to the 2 instrument consortia for 25% of the total observing time, going back to the 2 instrument consortia, 12.5% going to XIFU. There will be open time for 65% of the time. There will be calibration time and DD time. Now, for the key programs, there will be, they will account for 40% of the total observing time.
Okay.
And the rest will be geotime.
Okay. So thank you very much, Didier.